In this section, you will learn some examples concerning change of temperature and change of state. First, you are given specific heat capacity of water Cw, specific heat capacity of ice Ci, specific latent heat of fusion of ice Lf, and specific latent heat of vaporization of water Lv. Question number 1. Find the energy required to change 0.6 kg water from 20 degrees Celsius to boiling point. The energy needed is E equal to mc delta T equal to 0.6 times 4,200 times boiling point of water is 100. Therefore, the delta T is 100 minus 20. And the answer is 202 kilojoules. Question number 2. 300 grams of water at 12 degrees Celsius is cooled in the freezer of a refrigerator. Find the energy released when the water is cooled to its freezing point. The freezing point of water is 0 degrees Celsius. Therefore, the energy released E will be equal to mc delta T, where delta T is the temperature decreased. E equal to 300 grams, the mass we change into kilogram, which is 0.3 kilogram. Okay? C of water is 4,200. Okay? And the temperature decrease will be 12 minus 0. Therefore, the energy released in this case will be 15,120 joules. Question number 3. Find the energy needed to vaporize a cup of water of mass 0.5 kg at 32 degrees Celsius. This question involves 2 stages. For stage 1, energy is needed to change water from 32 degrees Celsius to water at 100 degrees Celsius. The energy involved is E1. Next, additional energy E2 is needed to vaporize all the waters to steam at 100 degrees Celsius. Therefore, the energy needed is equal to E1 plus E2, which is equal to, for E1 it is mc delta T, for E2 is mL, okay, for vaporization this is LV. E equal to 0.5 times 4,200 times 100 minus 32 and plus 0.5 times LV, which is 2.26 times 10 to the power 6. The answer for E should be 1.27 times 10 to the power 6 joules. Question number 4. 240 grams of water at 25 degrees Celsius is put inside the freezer of a refrigerator. The water changes to ice at -8 degrees Celsius. Find the energy released by the water. These questions involve 3 stages. The stage 1, the water at 25 degrees Celsius has been cooled down to water at 0 degrees Celsius first. In this case, the energy released is E1. Next, the water at 0 degrees Celsius is cooled down until it all changes its state to ice at 0 degrees Celsius. And the energy involved is E2. Lastly, ice at 0 degree is further cooled down to ice to be -8 degrees Celsius. And in this case, the energy released by the ice is E3. Therefore, the total energy released by the water would be E equal to E1 plus E2 plus E3. For E1, it is equal to mc of water delta T of water plus E2 is equal to m times specific latent heat of fusion of ice plus E3 is mc of ice delta T in ice. The result is change mass from gram to kg first. It would be 0.24, okay? And we extract the mass in all the terms outside. Therefore, we have 0.24 times Cw 4200. Okay, the change in temperature in water is 25 minus 0, and plus LF is 3.36 times 10 to the power 5 plus CI is 2100 times change in temperature in ice is 0 minus -8, which is 8 degrees. Therefore, the total energy released by the water is 109 kilojoules. Question number 5. Steam at 100 degrees Celsius is passed into a cup of water of mass 2 kg at 25 degrees Celsius. Find the mass of steam needed if the temperature of the mixtures becomes A. 100 degrees Celsius water, B. 80 degrees Celsius water. First, let the mass of steam needed be m. For part A, steam at 100 degrees Celsius condensed to water at 100 degrees Celsius. In this case, the energy released is E1 equal to mLV. At the same time, the water increased its temperature from 25 degrees Celsius to water at 100 degrees Celsius. The energy absorbed by the water would be E2 equal to m pi Cw delta T. Assume there are no energy lost to surrounding. We have energy released by the steam E1 equal to energy absorbed by the water E2. Therefore, we have mLV equal to m pi Cw delta T. We have mLV is equal to 2.26 times 10 to the power 6 equal to M pi is 2, Cw is 4200, and the temperature rise of water is from 25 degree to 100 degree. Using this equation, we can find M. Mass of steam lit is equal to 0.279 kilogram. For part B, since the final temperature of the mixture is 80 degrees Celsius water, the steam will first change to water at 100 degrees Celsius and release energy mLV. Next, the water will further decrease its temperature from 100 degrees Celsius to 80 degrees Celsius. In this case, there is also energy released. We call this energy release equal to mc delta T. Okay? Therefore, in this case, the energy released by the steam during these two steps is mLV plus mc delta T. Okay? Next, the energy absorbed by the water will be changed from water at 25 degrees Celsius to water at 80 degrees Celsius. Okay? In this equation, we have energy released by the steam is still equal to the energy absorbed by the water. However, we need to add mCW delta T, okay, into the left hand side. Okay, that is to say, besides M times LF, we have plus mCW is 4200, and the temperature decreased from 100 degrees Celsius to 80 degrees Celsius. Okay, is equal to 2 times 4200 times, this is not 100, instead it is 80 minus 25. Therefore, in part B, the result will be the mass of steam required equal to 0.197 kilogram. Question number 6. A liquid is kept boiling by 250 watt immersion heater. The liquid boils away at a weight of 2 times 10 to the power -4 kilogram per second. Find the specific latent heat of vaporization of the liquid. First, let the specific latent heat of vaporization of the liquid be L. Notice that kept boiling means that the liquid is changing its state to gas. The energy released by the heater will be PT, and the energy absorbed by the liquid during its change of state is mL. If there is no energy loss to surrounding, all the energy released by the heater will be equal to the energy absorbed by the liquid in changing its state. Therefore, we have PT equal to mL. Next, change the equation to be P equal to M over T times L. Power is given 250 watt, and mass over T is also given, which is equal to the weight at which the liquid is boiling. That is M over T equal to 2 times 10 to the power -4 L. Therefore, the specific latent heat of vaporization of the liquid would be 1.25 times 10 to the power 6 joules per kg.